Every generation returns to a fundamental question, though its form may change with the times. How do we produce energy without causing harm to the world on which we rely? In recent years, this question has been distilled into a single term: green. This label is omnipresent, found on everything from electricity bills to city buses, and deeply embedded in national energy strategies and climate pledges. Yet, the term green has become so overloaded with meanings that it often obscures more than it reveals. A system may be labeled green not because it's truly clean in a physical sense, but because it fits within a policy definition, a regulatory category, or a transitional compromise. Consider the myriad systems branded as green. Many of these still emit carbon dioxide or other pollutants. They are deemed greener not because they are entirely clean, but because they are perceived as better than the alternatives, easier to integrate into existing infrastructures, or simply politically convenient. To truly understand what is sustainable, what is merely transitional, and what is fundamentally impossible, we must move beyond slogans and return to first principles. Understanding what energy is, where it originates, how it is converted, and why some ideas can scale while others cannot. When we examine energy through the lens of physics rather than marketing, a consistent pattern emerges. Certain technologies succeed not because they are clever, but because they align with large, continuous natural energy flows. Others fail not due to a lack of imagination, but because they confront hard limits that no amount of engineering can sidestep. Energy, contrary to some misconceptions, is not a substance. It is a property, a capacity to do work or cause change. It can manifest as motion, heat, light, chemical bonds, or even mass itself. Crucially, it cannot be created from nothing. This is not a matter of debate in scientific circles. It stands as one of the most thoroughly validated laws in human knowledge. Every power system humanity has ever devised adheres to this principle. The variations lie in the energy's origin, its density, and the practicality of capturing and converting it. Most conventional electricity production follows a similar macroscopic structure. Something moves, that motion turns a turbine, the turbine spins a generator, and electricity emerges. Coal, gas, nuclear fission, geothermal heat, wind, and flowing water all operate on this principle, differing mainly in what causes the motion. Solar photovoltaics, however, stand as a significant exception. They do not defy thermodynamics, but instead convert energy at a different level. Solar panels move electrons directly using light, bypassing the need for heat, steam, or rotating machinery. This distinction is what makes solar transformative and explains why many clever ideas do not scale. Consider the case of biomass and waste incineration. When countries like Denmark burn biomass or municipal waste to generate electricity, they emit carbon dioxide into the atmosphere. Chemically and physically, CO2 from burning wood or waste behaves identically to CO2 from burning coal or oil. The atmosphere makes no distinction regarding the carbon's origin. Biomass is often labeled renewable due to a carbon accounting argument. Plants absorb CO2 during growth, so burning plant material is seen as returning that carbon to the air rather than adding new fossil carbon. The issue here is timing. The CO2 is released immediately, while its reabsorption, if it fully occurs, takes decades. During that interim, the carbon contributes to warming just like any other carbon. Waste-to-energy incineration adds another layer of complexity. Modern waste includes plastics, which are fossil fuels in solid form. Incineration may reduce landfill volume and mitigate some methane emissions, but it does not eliminate pollution. It transforms the waste problem into an emissions issue and locks in an incentive to burn materials that might otherwise be reduced or recycled. These systems are best understood as transitional tools under constrained conditions. They can provide dispatchable power and address waste management challenges, but they are not clean in a strict climate sense. Turning to natural gas, often presented as a cleaner alternative to coal or diesel, we see a similar confusion. Burning gas typically produces fewer particulates and less sulfur pollution than diesel, which can enhance urban air quality. This is one reason some cities transition to gas-powered buses. Yet, from a climate perspective, gas is not green. Natural gas is predominantly methane, a greenhouse gas drastically more potent than CO2 over short time frames. Methane leaks can occur during extraction, processing, transport, refueling, and even from the vehicles themselves. Even modest leakage can negate much of the climate advantage over diesel. This underscores a common misunderstanding. While reducing visible pollution and improving city air quality are real benefits, they do not equate to climate friendliness. Air quality improvements are local, climate impacts are global. A technology can be cleaner on the street while still contributing to atmospheric fossil pathways. Solar photovoltaics, often grouped with other renewables, actually stand apart. They do not rely on heat, pressure, fluids, or motion. Instead, they depend on the photovoltaic effect, a quantum process where photons transfer energy directly to electrons inside a semiconductor. A solar cell typically contains a p-n junction, creating an internal electric field. When sunlight strikes the semiconductor, photons can liberate electrons. The internal field separates the charges, producing a voltage. If a circuit is connected, electrons flow as current. This represents direct energy conversion, light to electricity, with no turbine in between. This is why solar technology can be extremely reliable mechanically and last for decades. Its primary limitation is not mechanical wear, but intermittency. The sun, a vast external energy source, is not continuously available at a fixed intensity everywhere. As solar use grows, storage and grid balancing become the bottlenecks. Fusion, often heralded as a future technology poised to revolutionize energy generation, in reality changes the heat source, not the macroscopic conversion chain. Fusion reactions are quantum processes that convert a small amount of mass into energy, but the energy manifests as fast particles and heat, not as ready-to-use electricity. To generate electrical power from fusion, the system still needs to capture heat, transfer it to a working medium, generate steam or another driving fluid, spin turbines, and run generators, just as fission plants do and just as fossil plants do. The difference lies in the fuel and emissions profile, not the overall thermodynamic architecture. Projects like ITER aim to demonstrate sustained fusion conditions and net energy gain at the reactor level. Even if fusion becomes commercial, it will be an advanced heat engine at scale, not a turbine-free miracle. Nikola Tesla, an extraordinary engineer whose achievements reshaped the electrical world, did not discover a way to produce energy from nothing. The enduring myth that Tesla had free energy ideas suppressed by powerful interests is a cultural narrative, not a scientific reality. Tesla explored wireless power transmission and high-frequency systems. Yet wireless transmission is not synonymous with energy creation. A transmitter must still generate power from a source and then deliver it elsewhere. The reason Tesla's grandest transmission concepts did not become the backbone of global power was not due to conspiracy, but rather issues of efficiency, loss, interference, and economics. The allure of energy from nothing is understandable as it promises abundance without trade-offs. However, the physical law of conservation of energy is unyielding, and every credible experiment ever conducted reinforces it. Any device that appears to generate energy without an input is either misunderstanding its inputs or mismeasuring its outputs. Living systems, while they absolutely contain and use energy, do not contain extractable surplus power. Cells store energy chemically, primarily through molecules like ATP, and maintain small electrical potentials across membranes. This electricity is used for signaling and internal regulation, not for delivering external power. Attempting to extract meaningful electricity from cellular processes would disrupt the processes vital to a cell's survival. A dead cell yields nothing. While microbial fuel cells exist and can generate tiny currents using certain bacteria, the power density is far too low for grid-scale energy. Such systems are best suited for niche applications like sensors and wastewater treatment, not civilization-level power. Life is not a hidden battery. It is an energy consumer optimized to use what it has with minimal waste. Gravity is a mechanism that converts stored potential energy into motion, but is not in itself an energy source. In hydropower, the sun drives evaporation and precipitation, water accumulates at height, and gravity allows it to fall through turbines. In pumped hydro storage, electricity is used to pump water uphill when supply exceeds demand. Later, gravity returns that stored energy by sending water back through turbines. This is one of the most mature and scalable forms of grid storage in existence. Future gravity-based storage might involve lifting heavy solid masses instead of water. The principle remains the same. Energy must be put in before it can be taken out. Gravity functions as a durable battery, not as a generator of free energy. Some natural phenomena, like gravitational waves and earthquakes, involve staggering energy. However, neither is usable for power generation. Gravitational waves interact so weakly with matter that detecting them requires instruments sensitive to changes far smaller than an atom. The energy that reaches Earth is effectively irrelevant for harvesting. Earthquakes release energy suddenly, unpredictably, and destructively. Their power arrives in chaotic impulses that cause damage. Any system designed to couple strongly enough to extract meaningful energy would likely be destroyed by the very event it seeks to exploit. Moreover, the long-term average energy availability is low and unreliable. Power systems require predictable flows, not catastrophic spikes. Harvesting electricity from pressure, footsteps, or raindrop impacts is physically possible. Piezoelectric materials can generate voltage when stressed. Such methods can be useful in specific contexts, particularly for powering low-energy devices or sensors without batteries. However, these sources cannot scale. The energy contained in a footstep or a raindrop is small, and capturing it efficiently is challenging. Even with optimistic assumptions, the total harvestable energy is negligible compared to what modern buildings, industries, and cities require. These technologies might power a sensor network or an LED display, but they cannot meaningfully contribute to national grids. If pressure harvesting were a viable solution, airports and crowded streets would already function as power plants. They do not, because energy density sets a ceiling. Across these discussions, a simple and strict pattern emerges. Technologies scale when they can tap energy flows that are continuous rather than impulsive, directional rather than chaotic, and dense enough to justify large infrastructure. Sunlight fits these criteria. Nuclear binding energy does as well. Wind and water, driven ultimately by solar heating and gravity, can also scale. Many alternative ideas fail because they attempt to build civilization-scale energy systems from sources that are diffuse, intermittent in the wrong way, or too weakly coupled to matter. Low energy density cannot be overcome with cleverness alone. Humanity's energy future will not be built on miracles. It will be built on a small set of energy realities that physics permits to scale. Solar will dominate, both directly through photovoltaics and indirectly through wind and hydropower. Nuclear fission will remain crucial where high density and reliability are essential. Fusion may eventually become another high-density heat source, but it will still operate through conventional thermodynamic conversion. The most critical factor in a renewable heavy world will be storage and grid management. Batteries will play a significant role for short-duration balancing and electrified transport. Pumped hydro and gravity-based storage will remain foundational where geography permits. Hydrogen and other fuels may serve as long-duration storage and industrial feedstocks where direct electrification is challenging, albeit with efficiency penalties. Many systems branded as green today are transitional pathways rather than end states. That is not a moral failing, it is an infrastructure reality. Societies change slowly. The decisive move is to align policy and investment with what can scale cleanly over decades rather than merely reduce harm in the coming years. In conclusion, humanity does not lack energy ideas. It suffers from confusion over which ideas adhere to physical reality at scale. The laws of physics are not barriers to overcome. They are the map of what is possible. Once we stop looking for energy in everything and instead design civilization around the few energy sources that truly scale, the future becomes not only clearer, but achievable.